In this video, we're going to go over some of the complexities involved in making a fault-tolerant distributed system. We're going to use an e-commerce system here as our example because we want something that has a decent number of moving parts but isn't too complex. So our base architecture diagram for our e-commerce platform is going to consist of an API, a database that stores information about our products and our users' purchases, and some payments processor that we have to interact with, and that's going to be a third-party service that's handling our payments. If you want to learn more about how all of the systems involved in this discussion actually work at a low level, you should check out our Systems Fundamentals course on interviewpen.com. So now we're going to dive into every single one of these pieces and talk about how it can fail and what we can do to recover. This is a really common thing that an interviewer will ask you about in a system design interview. You'll often have to take a complex system and talk about all the ways that you can prevent it from failing and recover from the unexpected. So to start, let's dive into each one of these components and talk about how it can fail. The first single point of failure we're going to see here is the API. If we have a single API server here that our user is interacting with, if this API server fails, our user is completely unable to interact with our system. So to solve this problem, we're simply going to duplicate our API, so we're now going to have 3 versions of our API that are all running the exact same code. Our API should be a stateless service, meaning that it doesn't really matter which version of the API we're interacting with. All of the inputs and outputs of this API should remain the same. Now, in order to tell our user which API to interact with, we're going to need some load balancer that will direct our users to the correct API node. So if our user hits the load balancer, they should be directed to whichever node has the least traffic and is online at that time. So now if one of our API nodes goes down, our load balancer will quickly notice that, and it'll be able to redirect our user's traffic to any of the other 2 online nodes. This also has the advantage of scaling our API, meaning that each individual node only has to handle a subset of the traffic for our whole system. The next problem we encounter here is the load balancer. If we have a single load balancer and this load balancer fails, we have the same problem that we had before. So to solve this problem, we have to introduce a slightly less clean solution that we can take advantage of in the event of a load balancer failure. So to start, we'll introduce 2 load balancers, and each of those will have a separate IP address that our user will use to interact with it. So in this example, if our user requests 1.2.3.4, they'll go to this first load balancer, and if they request 5.6.7.8, they'll go to this second load balancer. Now we'll configure our DNS records for our entire system such that the DNS server will return 2 different IP addresses for these 2 load balancers. So what this DNS server is going to do, when we pass it the domain name for our server, for example, myecommercesite.com, our domain name will translate that into this set of 2 IP addresses. In general, when we receive 2 IP addresses like this from our DNS server, the client, i.e. your computer, is responsible for picking one of these IP addresses to use. It'll either use a round-robin approach, or simply pick the first one. However, generally clients have functionality built in such that if one of these IP addresses isn't available, it'll go on to the next one. So this means that if one of our load balancers fails, our user will try to access it, realize it's not available, and then fall back to the second one. This isn't a great solution for 2 reasons. First of all, we're introducing latency for our clients because we now have to make this failing request first before we can make the request to the functional load balancer. So if one of our load balancers is down, while our users will still be able to access the system, they will have increased latency. Secondly, DNS is often cached in a lot of places. So this means that we have a lot less flexibility over introducing new load balancers or removing them. So if we wanted to do some update and we needed to bring one of these load balancers offline, we'd need to make sure that we took it offline quickly and then restored it with the same IP address. Our APIs, on the other hand, are much more dynamic, and our load balancer can simply be updated with the set of IP addresses of all of these API nodes, and that can be quickly changed and it's not cached anywhere on our clients. It's also worth noting that most computers are configured to use 2 DNS servers. So while these DNS servers aren't under the control of our system, if one of them fails, the client will know to fall back to a second one that's more likely to be available. So the next single point of failure we're going to take a look at is this database. Of course, if we have a single database node and that one node fails, our API will still be accessible, but it will be unable to access any of the data for our users. This will have a similar solution to our API by simply creating multiple copies of the database. However, we're introducing a little bit of complexity here because our data has to be replicated across all 3 of these nodes. For example, if one client writes some data to the first node and then another client tries to read it from the second node, we need to make sure that there's logic in place to replicate the data from the first node to the second and third nodes. So all of these nodes are going to be communicating with each other behind the scenes. The result of having these copies of the database means that our API can then access any one of these database nodes and get access to the data that it's looking for. This has the advantage of both fault tolerance and distributing the read capacity of our database. In order to enable our API API to know which database it should access, we're going to use some sort of private DNS system or a service discovery system. Regardless of the option we choose, this service will be responsible for responding to requests from the API about what databases are available. So this service will be responsible for consistently health checking our database and making sure that the different nodes are available. If one of them isn't available, it'll know not to tell the API about that particular node. This means that if one of our database nodes fails, all of the data will still be copied and replicated onto the other two nodes. Our service discovery will quickly realize that that node is not available, and our API will start falling back to those second two nodes. So the final single point of failure that we have to think about here is the actual payments processor. This is a much harder problem to solve since this service is a third-party system that isn't under our control. However, most third-party services that offer APIs to large companies will also come with SLAs, or service level agreements, that define an amount of uptime that they're required to have for their service. So for example, our e-commerce platform might sign an agreement with this payments processor saying that the payments processor is required to be online 99.9999% of the time. If that service level agreement isn't acceptable for our use case, we might consider using a second service provider that we can fall back to if the first one isn't available. However, this does introduce a lot of complexity as different service providers will have different APIs. So we've eliminated most of the single points of failure in our system. However, we still have to think about some of the larger failure modes that can occur. One really important thing to consider in this situation is server racks. So if we have two racks of servers, each of them has a network switch connecting all the servers in that rack together, and we have one rack for API servers and one rack for database servers, this seems fine, but if somebody trips over the power cord for one of these racks and knocks out the entire set of servers, we're going to lose our entire database, and our replication strategy doesn't really help us at all. So it's really important when designing a system like this to make sure that we're distributing our replicated systems across multiple racks so we can handle a failure of an entire server rack. So in this new case, if we knock out an entire server rack here, we'll still have half of our API nodes available and half of our database nodes available, and our service will continue running. In this second example, we've also introduced a redundant network switch in the rack, and this will ensure that if one of the network switches happens to fail, it won't knock out the entire rack, and we'll still have networking to all of our servers through the second switch. One final consideration to make is handling a failure of an entire data center. So to handle this type of failure, we want to make sure that our service is distributed across at least two different regions, so that if one region experiences a natural disaster or a power outage or something of the sort, we won't lose our entire service, and our users can fall back to another region. So you can see in this diagram that our service remains pretty similar to the way it was before. However, our two load balancers that we have are now in two separate regions. So based on this DNS request, our client will be able to pick which region it goes to, and then from there we have our same redundancy within that data center. This means that even if an entire region is knocked out and we lose an entire data center, our clients will still be able to fall back to a different region, which will have its own set of redundant systems. So at this point, we've come up with a pretty good solution that should handle most failure modes. Of course, there's no perfect solution, and I'd absolutely encourage you to dig deeper into how all of these systems work so that you're adequately prepared if asked about these types of things in an interview. If you enjoyed this video, you can find more content like this on interviewpen.com. We have tons of more in-depth system design and data structures and algorithms content for any skill level, along with a full coding environment and an AI teaching assistant. You can also join our Discord, where we're always available to answer any questions you might have. If you or a friend wants to master the fundamentals of software engineering, check us out at interviewpen.com.